Hey, Tony, are you ready?
Yes, I'm ready.
Okay. Yes, good morning, good afternoon, and good evening. This is Paul Liu from NC State University. Welcome you again to this World River and Delta System Source to Sink webinar series. Today, we are very happy to invite Professor Tony Rodriguez from University of North Carolina at Chapel Hill come here talk about coastal sedimentation across North America. So before I introduce Tony, once again, all our previous talk have been archived on the YouTube channel. So as you can see, free to use for the research, for education. And also we also have a Twitter account, Source to Sink. You are welcome to follow us. So we will announce all the coming talks. And next Wednesday, next week, we have Elder Maramontes from University of Bremen, Germany, come here talk about how can ocean currents affect the transfer of sediment to the deep sea. She is expert in terms of turbidity current transport, internal wave, impact sediment delivered to the ocean. So please mark your calendar coming here next Wednesday. And so Tony, as I mentioned, is currently a full professor at the UNC Chapel Hill Institute of Marine Science. And also they have a new department. The new department is a combination, is merged, called Earth, Marine, and Environmental Science. So Tony got his PhD from Rice University, working with a famous professor, Professor John Anderson. John also gave a talk a couple. And of course, Tony's research interest in mainly is marine coastal geology, sedimentation, stratigraphy, particularly response to the sea level, storm, and human impact. So I think, Tony, now you can share your screen.
All right. All right. Down here. Okay, everything look all right?
Good.
So yeah, if things start going awry, please interrupt me and I will correct the problem or do the best I can. So thanks so much for inviting me, Paul, and organizing this whole seminar series. It's been really great. Unfortunately, I teach a class at this time, so I haven't been able to see that many of the talks, but I hope to look at them at the YouTube channel. So before I begin, I just want to make some acknowledgements and get the acknowledgements out of the way up front before I forget at the end and run out of time. So Brent McKee, everything I'm going to be presenting today is work that I've done with Brent McKee, and all the samples that we process for lead 210, it's done in Brent's lab. And, really he taught me and all of my students everything we know about lead 210. So thanks, Brent. And he's really a co-author on this talk. And the other person I want to acknowledge is Molly Bost. She's a PhD candidate and she's working, this is her last year of her PhD. And I'm going to be presenting towards the end some unpublished data that's part of her dissertation. And then all of these folks out here have worked on data sets that I'm going to be presenting today. Charlie Deaton, Carson Miller, Anna Atencio, those three received their master's degree years ago. Robin Mateus, I'm going to go over some of his work from his PhD, maybe 10 years ago now. Rich Mahoney was a technician and helped collect a lot of the data I'm going to be talking about today. And Dr. Joel Faudry, who's a fisheries ecologist. And later on, I'm going to be talking about sedimentation in tidal creeks, and those are primary nursery areas. And so Joel takes some of the work that comes out of our lab and sees how that's affecting different communities. So some funding. I wouldn't say a lot of this work I'm presenting is lucratively funded, but we have some funding from the University of North Carolina, at least through a class that Brendan and I taught, the NC Policy Collaboratory, the Marine Fisheries, the Division of Marine Fisheries in North Carolina, and North Carolina Sea Grant. And I also put a bunch of citations here because the first part of this talk deals with coastal sedimentation around North America, and it's really a data mining study. And so if you want to go back and look at some of the details from the original papers that we grabbed data from, this is one place you can do it. And I showed some of these citations later on too. Okay, so the primary question today that I want to address are most coastal areas starving for sediment? And clearly, we've constructed many dams and built reservoirs in North America, and this map is just showing the United States. And it's color-coded so that the smaller dams are in blue, medium-sized dams in green, and the larger dams are in red here. And if you look at this graph here, this is number of dams constructed in the US, and this is per decade down here. And you can see that the number of dams, they really increased around in the 1950s and then started to peter off to present. And these reservoirs are definitely trapping sediment behind them and within them. But the question I want to address is, even though the reservoirs are trapping sediment, does that necessarily mean that all coastal areas are sediment starved? Like this photo is showing down here of a salt marsh in North Carolina that definitely is not keeping up with the rate of sea level rise and is somewhat falling apart. And there are lots of examples like this all along the coast of the United States. So if we look at hydrologic models and published studies, they show that there's a decrease in the suspended load of rivers, and largely due to sediment retention behind dams. And this is a popular study, which I've cropped just part of the figure from Savitsky et al. 2005. And this is looking at the difference between pre-industrial revolution and modern river loads. And we're looking at the colors here in red for some larger systems. It's a huge reduction in sediment load. But then there are lots of these blue circles here, which is actually an increase. And there are lots of these dots here that you can hardly see all along the coast with these smaller systems. And the model didn't have the resolution to say whether it was a reduction or an increase, so -5 to 5. This study over here zooms in on this part of the North American coast that I'm pointing at. So a little bit of South Carolina and Georgia. And they compared pre-European, which is illustrated with the size of these arrows here, the brown arrows, with pre-dam. So now humans have come in and we've clear cut, maybe for farms or for buildings. And we've got this giant yellow arrow, so an increase in load. And then post-dam is here. And again, it's illustrating that we've trapped sediment behind reservoirs and that the flux to the coast has decreased. Other studies look at river gauges, and this is one from Weston 2014, and they show that the suspended sediment load is declined at 25 gauges along the east coast of the United States and the Gulf Coast. And that's because of retention in reservoirs. And all of these gauges, this is the most downstream gauge. But each one of these gauges, it's still located, about 10 to 15 kilometers upstream to where these rivers are discharging into coastal systems like estuaries or the inner shelf. And so all the red circles, the size of the arrow, or the size of the circle is scaled to the decrease if it's red, and the increase if it's blue. And just a few systems here, they noticed an increase. So then they took this information and then extrapolated it to the coast. So we're moving from New England to the western Gulf of Mexico in this graph. And they compared it with relative rates of sea level rise and really showed that, or tried to argue that these coastal systems or wetlands, their vulnerability to sea level rise is really increasing as a result of the trapping of sediment behind dams. Now, it's difficult to look at Streamload data and say something about whether coastal areas are being starved of sediment or not. And what makes it difficult is that these records are really short term. And so if we look at a bunch of papers here in purple, orange, and blue on this side, this is showing the duration of river gauge records that are measuring load. And you can see it's really only a few decades. This study here, it's based on 35 river gauges, and we're just looking at a couple of decades of data. And even within these bars, some of these bars are quite large, but really the whole time frame isn't even being sampled. So a lot of these stations are only sampling, less than 5% of the active time period. And again, the stations are positioned really far inland from the coast. So it's possible that there are other sources between these gauges and the coast that are supplementing loads. Okay, so some of the questions, we're going to get into the data now. So are estuaries truly experiencing a decline in sedimentation? So that's something I hope to address today. And is sedimentation keeping pace with relative sea level rise? Okay, so how do we do this? So this study was part of a class that Brent and I ran where we surveyed the literature, and we came up with about 25 sites across North America, and they're all shown on this map here. And of these sites, 18 are estuaries. So these are all subtidal depot centers. So 18 are estuaries, 6 are on the intercontinental shelf, and one of them is the subaqueous Mississippi Delta. And again, so here are some of the sources, and here are the names of all of the sites. So as we're culling through the literature, we realized that we needed to have some criteria of what papers to include in the study. And so the first criteria that we used is that it needs to be a peer-reviewed article, and it has to present raw data so that we can manipulate those data. The sites need to be undisturbed. So in all of these papers, they had supporting information, grain size, bioturbation indexes, X-rays, and so information that helps, or that they use to argue that their cores are not mixed. And in many of the papers, they collected more than one core from each depot center, and we only chose one of those cores, and we tried to choose what we thought were the best ones. So they had the longest record, the least disturbed record. And then we're using lead-210 to create geochronologies. And so all of those papers, the lead-210 profiles, they needed to have at least 3 data points before and after 1950, where that human impact really began to increase, so we could capture that. And also the profiles have to have a complete lead-210 inventory. And the reason is because we're using this model to create the geochronologies, this constant rate of supply model, which allows sedimentation rates to vary, but it hinges on having a complete inventory. So we need to make sure that all the profiles go down to supported levels of lead-210. And some of the studies use this other model where you just get an average rate, and we would resample those data and reprocess it in the CRS model. If you want more information on the models that we used, we're really just using information from this paper down here, Sanchez Cabeza and Ruiz Fernandez 2012, and they present spreadsheets that you can use to put your data in and create chronologies. Okay, and finally, we wanted to compare sediment accumulation rates with relative sea level rise. So we went in, so of the sites, of the 23 sites where sea level is rising, we went in and sampled the closest tide gauge for its previous 50-year record. And this is just showing the range in sea level rise rates in millimeters per year that we included, or that is incorporated in our 23 sites. Yeah, so 2 of the sites, sea level wasn't rising. Okay, so what do those data look like? Here it is all smashed together on a scatter plot. So all 25 sites, each data point is shown. And so we're looking at MAR, so mass accumulation rates, and this is in grams per centimeter squared per year. And now we're looking at time. And I just wanted to highlight 3 or 2 end members and 1 kind of middle type site. So Florida Bay had some of the highest mass accumulation rates. Corpus Christi Bay is one of these that's in the middle, and it's just fed by kind of a medium-sized river, the Nueces River. Nastapoca Sound, far in the north, is kind of a weird one. It doesn't have direct river influence, but it does have some supply from adjacent rivers, and a lot of erosion from permafrost material is contributing to this record. And we use 1950 as a break line in all the data. So we compare pre-1950 with post-1950. And I'll get into some of the details in maybe 3 of the sites later on. So, okay, so another way of looking at that scatter plot is this way. So comparing pre-1950 data with post-1950 data in orange. And so in this chart, we have the site name, and this is the minimum mass accumulation rate and the maximum mass accumulation rate here. And then these bars represent the pre-1950 and post-1950. And you can see for just about every one of these sites, mass accumulation rates increased during the more modern time step. So from 1950 to when the core was collected, as opposed to the earlier one. And 2 of these sites in the Gulf of Mexico, it's not statistically significant, but there was still an increase. So if we dive in a little bit deeper so that we can see some individual sites, you can see that there's not really anything magical about 1950, but like most science projects that are looking at data from a particular place, those data are telling a unique story that's particular to where it's collected. So for example, this is the Gulf of Tehuantepec in Mexico, so site 21 right here. And on the scatter plot, that's highlighted in purple. And another way of looking at the data, if we zoom in on it and we account for some of the error in time and some of the error that we're seeing in accumulation rate, you can come up with this type of a plot. So time and mass accumulation rates. And then here's 1950. And you can see that there was an increase if we compare these data post-1950 to pre-1950. But the data is more rich than that. You can see right at 1950, actually, there was constant mass accumulation rates. And then it starts to increase again after 1980. And the authors of this paper, Ruiz Fernandez et al., 2009, they argue that economic development and its associated population growth in the coastal zone explains this increase in mass accumulation rates. Okay, another one, a site that Paul and I know well, so the Pamlico River estuary in the US, and that's right here. And again, I've highlighted it on the scatter plot in green, and here it is in that same bar format. And you can see here we've got this peak around 1920, and then it goes back down, and then another peak around the 40s, and then this overall climb as we move into the 60s and 70s. And the authors of this paper, Cooper et al., 2004, they argue that this increase is a result of changes in land use and increasing population on the coastal plain. Okay, the final example, still moving up the coast, Pocomoke Sound, which empties into Chesapeake Bay in the US. So right here, again, highlighted in orange. This site, similar to the previous one, it shows this kind of flattening out, but an increase around the 20s to 60s. And then since 1960, this overall increase. And the authors of this paper, Holmes and Merritt, 2004, they argue that this increase is due to urbanization, agricultural activities, and bank erosion of the river. Okay, so if we look at the data in a little different way, over here we have post 1950 mass accumulation rates. So this is the recent part of the records, and the older part of the records down here on the x-axis. So this is pre-1950 mass accumulation rates, and each dot is plotted as an average with standard deviation. And we've coded them so that East Coast, Florida, and Alabama are the squares. The circles are Louisiana and Texas, and the diamonds are the West Coast. And you can see overall, all of these sites are falling on the 2-to-1 line, a little bit above, a few sites within error, but it's showing that there's been a doubling in mass accumulation rates since 1950. And over here, this is sediment accumulation rates. So the unit's a little bit different. So this is millimeters per year. Thinking about how the bottom is accumulating sediment in terms of millimeters per year, not grams per centimeter squared per year. And again, organized the same way. So here's the more recent part of the record and the older part of the record. And again, the points are really clustering along this 2-to-1 line. So does everything I've presented, so there's an abundance of sediment reaching these depot centers more in the post-1950 time period than the earlier period, that could just simply reflect that older sections of the core span longer periods of time. And when you do that, when you make those comparisons, if you're comparing a longer time period with a shorter time period, that longer time period might have more breaks in sedimentation in it. It might have erosional surfaces in it. And that could be the reason why our earlier values for the pre-1950 time period are less than our more recent values. But I do want to mention that the original studies, they do argue that these cores are homogeneous and they're not mixed. And so they don't show evidence of erosional surfaces. But let's explore that a little bit further. Okay, so to do that, what we decided to do was go back in time. So we developed sediment accumulation rates at 1,000-year timescales for as many of the depot centers that we could. And that's what's shown on this map. So we did this for all of the dots that are coded in red. And Mobile Bay is an area. So we took information from a paper that came out of my group looking at Mobile Bay. And so you can image the Middle Bay sediment thickness here, and it's about 14 meters thick, and we have a core there, and we sampled that core at different depths and collected radiocarbon dates. And so from that information, you can calculate sediment accumulation rates, and now we're in centimeters per year at the 1,000-year time scale. And I'm comparing that in this graph with the lead-210 data, but for the older part of the lead-210 record, so 1890 to 1850 CE. And so here's the 1-to-1 line, and you can see most of the points are falling either on or slightly below that 1-to-1 line, indicating that over 1,000-year time scales, sediment accumulation rates were actually faster than they were if we compare it to this time frame here. So it's probably not that we have more breaks in sedimentation over the longer time scale in these settings. All right, so if we take this further, and this time I've shifted these points up a little bit because now I'm comparing the part of the lead-210 record that's just pre-1950 with the 1,000-year time scale sediment accumulation rate. So the points are now up higher here. And so why did sediment accumulation rates increase? And we think this is largely driven for this time period. It's accommodation driven. So something that happened at the end of the 1800s, early 1900s, is the rate of sea level rise started to increase. And that's what's shown from global tide gauge compilations, like what's shown up here from Garrels and Woodworth in 2013. And also locally, so here's an example from North Carolina, Kemp et al. 2011. You can see that increase between 1865 and 1892 in the rate of sea level rise. So we're creating more space where sediments can be deposited, and that's increasing sediment accumulation rates. So if we do the same thing, but now the green points, that's just looking at the post-1950 part of the lead-210 records. Now sediment accumulation rates are truly unprecedented, and it's more than what can be accounted for by just a change in accommodation space. And so something else that was going on after 1950 is populations in coastal counties really increased. And that's what's shown on this figure here. So for each site, we're looking at the record of population. And you can see that the most recent time step, so between 1950 and 2010, is when we had the largest increase in population in coastal counties. And this is a common proxy for changes in land use. Okay, so where's the sediment coming from? That's a good question. And it's somewhat outside what we could do with those data because we don't have sediment fingerprinting information. But we can explore that a little bit further. So these previous studies, they present this clear link between dam construction and a decrease in sediment load. I think I've shown that a lot of these studies are indicating there's some disconnect between the most seaward dam and the coast, because the coastal areas that we've looked at are actually increasing in mass accumulation rates and sediment accumulation rates. So there is some downstream source that's compensated for the losses that we've experienced behind dams. So river incision and bank erosion is one source. So maybe modified river flows have increased river incision and bank erosion, and lots of people have explored that. And this is just one study from North Carolina, Hupp et al. 2009, that's looking at the Roanoke system. And here's an image of the Roanoke. Here's Albemarle Sound. This is what the end of the Roanoke Delta looks like, or the outlet right by Albemarle Sound. And what they showed is that as you move from the coastal plain towards Albemarle Sound, bank erosion is increasing and floodplain deposition is decreasing. And that's because the flow is highly modified here. So we're not flooding these areas as frequently as we did. We're keeping the water in the channel, and we've increased erosion of the channel banks. And lower coastal plain rivers, they're also influenced by land use change. Now, this isn't a unique finding. Here are a couple of other papers. This was published in January of 2020. Global scale human impacts and delta morphology has led to net land area gain. And these studies, these authors showed they inventoried 11,000 deltas globally and showed that over the past 30 years, there's been a net land gain. And they attribute this to humans, and in particular, deforestation. And that deforestation induced an increase in river sediment supply. This is another study that was just published a few months ago in the journal Paleolimnology, and they did an inventory of 500 lakes worldwide, and that's what's shown on this figure here. And they argue that there was an increase in mass accumulation rates also right at 1950. And it appears they attribute that to watershed activities, so agriculture and urbanization. Okay, so let's transition a little bit and move away from North America perspective and focus in on North Carolina, where I've been working for a while. So I'm talking to you today from this location, about right where my laser pointer is. And we've been looking at small tidal creeks and rivers along this stretch of coast from Cape Lookout to Cape Fear for a few years now. And if you look at this digital elevation model, something that's really striking is this feature right here, which we call the Suffolk Scarp. And it does kind of a right angle and follows the coastline. This is the shoreline during the last interglacial period. So we have very low elevation, low relief land seaward of the Suffolk Scarp. The Suffolk Scarp is the largest topographic feature where I live. And this is really low elevation and low relief because it's essentially intercontinental shelf that's exposed or has not yet been flooded. And so all of this area is 1 to 2 meters above sea level. All right, so the first system I want to talk about is the Newport River. And that's highlighted here. This is a tiny little river. The drainage basin size is only 250 square kilometers. And it's mainly draining that old topography that formed on the Suffolk Scarp. So it's an old shoreline topography. And if we zoom in on the watershed and we look at this shaded relief map, you can see some of the old beach ridges on that Suffolk Scarp. So the drainage basin's outlined in white dashes here, and we've characterized the different land covers. And so in yellow, that's agriculture. In red, it's urban. And in green, it's silviculture or tree farming. And how that land cover has changed through time is shown in this graph here. So in 1958, it was just agriculture and a little bit of urban. And as we move towards present, you can see that tree farming or silviculture really came on the scene. And so much so that a little over 20% of the drainage basin is now covered in tree farms. So we have this, this pond that's in the middle of a tree farm. And we collected a core from this pond. And we also collected a core from the Newport River estuary out here. And we wanted to see if all this land use change has influenced deposition at these sites. And so if we look at up here, this is the Walker's Pond, which is an old mill pond, that record. And if we look at average sediment accumulation rates, you can see that it was 0.26 centimeters per year. And then right at 1964, it shifts to 0.87. So it triples. And 64 again is right when the silviculture operation began. And if we compare that to this core out here in the Newport, it shows a similar story. So right at 1964, sediment accumulation rates just about doubled. And so we wrote a paper about this and thought it was really neat, how connected, even though the maximum elevation of the entire drainage basin here might be 4 meters above sea level, this land use change is directly connected to the estuary. And so within the resolution of the lead-210 method, as soon as tree farming started, we saw a response in the estuary, and that response was an increase in sediment accumulation rates. If we look at the shoreline, that shows the same thing. So here's the Bayhead shoreline right here, and where it is where it was in 1958. And then if we look at this figure, that's 2006, and we've had this much growth in the shoreline. And we mapped many more shorelines, and you can look at how the area of the Delta Plain has changed through time. And the area increased significantly right at 1964 too. Okay, so on to Molly Boss' PhD work. So we wanted to look at some smaller systems. And so we've moved into tidal creeks. Lots of people's research programs are looking at, large river systems. We went in the opposite direction. So the smallest river systems out there are tidal creeks. And we chose 12 tidal creeks from here along the North Carolina coast to close to the city of Wilmington area down here. And we characterize these into 2 groups. So sites 1 through 5, we call these tributary incised valley tidal creeks. So remember, the topography is really low here. And so these drainage basins are really defined when sea level is lower, and the rivers develop their own drainage basins and drain this area that's exposed when sea level is lower. And then when sea level rose, we flooded that topography. And so to some extent, these drainage basins that we call tributary incised valleys are a relic from lower sea level. And then we have these systems between 6 to 12 down here that are mainly draining the topography of the Suffolk Scarp. And we call those coastal prism incised valley tidal creeks. And so this is just showing their size. So drainage basin size on the y-axis and relief on the x-axis. And so the maximum relief for 11 down here, it's 16 meters. And the largest drainage basin size of that site is only about 30 square kilometers. And we just moved down from there. So these are really small systems, but they've experienced a lot of land use change because remember, coastal populations have really boomed since the 1950s. And so to give you an example, here's Howe Creek, that's site 9 right there. And this is what the land cover looked like in 1959. And if we jump to 2016, you can see a lot of urbanization has occurred. And we can go back and forth a little bit. So put your eye on this area here that used to be forest, and now it's a golf course and a development. And then we went into each one of the creeks and we collected a core. And we collected this core right where the creek outlet starts to widen, where we thought we would have the best record. And we processed those cores for lead-210, and I'm going to show all of those data in just a second. So the land cover is not just 2 time steps. So we have land cover data just about every decade and a little bit more frequently for some from 1959 to 2016. And that's what's shown on this graph. So here 1 through 12 are the creek sites on the map. And each green box is where we mapped land use. And so if we look at the data set as a whole, here's sites, again, 1 through 12. So 1 up here and 12 down here. And we're looking at, in yellow is agriculture, red developed, green forest, cleared forest in brown, water and marsh in blue. And so this is what it looked like in 1959, lots of forest and agriculture. And then if we zoom to 2016, you can see that the sites down here, the biggest change has been development, largely because these are communities that service the city of Wilmington. Up here where I live, we don't have large cities, lots of silviculture and agriculture, and that was the largest land use change. So if we look at all of the lead 210 data, and I've organized it with tributary incised valleys. So all of these systems are these up here, and coastal prism systems are all of these down here. And we just look at all of the lead 210 data plotted on top of each other. Similar to the other study, they show that each site has its own story, but overall, the sites are showing an increase in mass accumulation rates, which is what I'm plotting here, through time. So after 1950, mass accumulation rates are higher than they were previous to 1950. So let's just look at two examples of these tidal creeks in a little bit more detail. So let's look at Futch Creek. So here's a digital elevation model out of the Futch Creek watershed. So we're looking at number 7 down here. So this little tidal creek. So I move that up here to the left. And what we're seeing, so here's time down here, and we're looking at land use change. And so you can see that, just between 1982 and 1993, that's when urbanization of that watershed started to take off. And if I overlay the mass accumulation rates from the lead 210 data on here, you can see right as urbanization started to take off, more material is being deposited on the creek bed. All right, Hewlett's Creek, that's site 11 down here. And here's a digital elevation model of that watershed. Something that's interesting about Hewlett's Creek is this feature that I'm pointing at. This is a Carolina Bay. So it's a depression. It has a high elevation rim. And this Carolina Bay has been developed. And so there's a big retention pond right in the middle of the Carolina Bay. This is one of our largest tidal creeks that I noted before. So the drainage basin size is about 30 kilometers squared here. Okay, if I move that to the upper left and we look at land cover change, this one's a little bit different. So Hewlett's Creek is a lot closer to Wilmington. So when urban sprawl occurred, people first started to develop this area in Hewlett's Creek. And you can see we have increased development since 1959 onward, and then it starts to level off. I mean, I think they've developed all the land that's possible. Greater than 50% of the watershed is developed past 1993. And if we look at the lead 210 data and mass accumulation rates, we're not seeing much of a response for this increase in urbanization. It's only after 1982 that mass accumulation rates really start to increase. And so remember, I've been saying, each one of these systems kind of has its own story. And so with Hewlett's Creek, we started to development began within this Carolina Bay. And with this retention pond, this did a great job of managing runoff and sediment. It's only until development started to move down to the lower part of the watershed that we start to see a response to the creek bed. Okay, if we look at all of the data and the way we were looking at these data with the North American systems, so this is the more recent part of the record, so 1950 to 2016 mass accumulation rates, plotted with the older part of the record, 1900 to 1950. You can see most of the mass accumulation rates or average mass accumulation rates plot along this 2-to-1 line, or at least above the 1-to-1 line, indicating that there is an increase towards recent times. And in many cases, that increase was a doubling. Okay, so trying to wrap things up. some summaries and conclusions. Hopefully I've convinced you that many coastal areas are not starving for sediment. I haven't really gotten to the part where I compare rates of sediment accumulation rates with relative sea level rise. So let's do that here. So for all those North American systems, so I'm plotting sediment accumulation rates after 1950 against relative sea level rise. And you can see all of the East Coast, Florida, Alabama, and West Coast systems are either on this 1-to-1 line or above it. Whereas the Louisiana and Texas are all below it. And so this is indicating that these are not sediment starved systems, but of course, Louisiana and Texas are, and they're seeing lots of loss of salt marsh as a result of this and large ecological impacts. So some places are sediment starved, as we know. And if we look at the tidal creek data set in the same frame of mind, so if we just look at these 1950 to 2016 sediment accumulation rates, I've highlighted the sites that are tributary incised valleys. So this line here is relative sea level rise in that part of North Carolina. So it's a little bit higher. It's about 3.5 millimeters per year. And those sites are highlighted in red, and they fall pretty close to the line, and in some cases below the line. So some of the sites aren't keeping up with the rate of sea level rise, but 3 of the 5 are. All of the sites near Wilmington, those coastal prism tidal creeks, are above the rate of sea level rise. And so all of these systems are filling in and shallowing, quite a lot. And that supports what communities are saying that live along those creeks and complaining that they're having trouble getting their boats in and out of their houses. So where do we go from here? Well, as I showed you with the tidal creeks, a lot of those sediment accumulation rates have actually gone back down again since that initial stress or urbanization. And we know sea level is on the rise. So I still think there's definitely a problem with coastal sedimentation. And a lot of these sites that plot above the 1-to-1 line, that might be short-lived, and they could easily fall below the 1-to-1 line. And the same is true for these tidal creeks, especially the ones where they're not experiencing urbanization. Those tributary incised valleys, those can easily fall below the 1-to-1 line. And then that's when we start, shifting habitats and having some adverse ecological impacts. All right, that was a lot. That's my last slide. So I'm ready for some questions. Should I keep this up or escape out? What do we do, Paul?
Yeah, stay on here. Okay, great, Tony. Is a great talk, and I'm pretty sure people have many questions. Okay, go ahead from the audience. If you have any question, just unmute yourself and ask Tony any question.
Yeah, I have a question.
Go ahead, Michael.
Yeah, so really nice set of studies. One thing that I wonder about for the increase in sediment post 1950 is I wonder about organic matter that's accumulating that may get eaten or burnt off as it drops down, so that your recent accumulation rates are inflated due to the organic matter that's not preserved in the older sediments. Do you think that's a problem or not?
So for the North American studies, I can't say all of those papers, but a lot of them, they did look at loss on ignition down core. And I can tell you, at least for all of the work that we've done in North Carolina, we do constrain the amount of organic matter. And within the lead-210 timeframe, it's pretty straight lined. I mean, there is a little bit more right on the top few centimeters, but then it goes fairly constant.
Right.
So I don't think that's explaining what we're seeing.
Yeah, I certainly didn't think it could explain all of it, but it might bias things. Okay.
Oh, thank you, Mike. So next, Yijun, you have a question or not? I saw Don Anderson also raised the hand. Yijun, you have a question? I saw you unmuted.
Yes, yeah. I thank you for your presentation. Very interesting about sediment and in the coast. From our studies on the Mississippi River, the lower Mississippi River, and the Atchafalaya River, we found pretty large channel erosion. So channel erosion in the lower Atchafalaya River is intensive in the past 4 decades. However, we also noticed the erosion trend has been becoming stabilized. So in the recent decades, it looks like the channel bed has been stabilizing. So in the long run, I'm not sure about, yes, I agree with you. There is a sediment source from the channel, and but the question is, in the long run, once the channel bed becomes stabilized, you will not have additional sediment or not sufficient sediment to feed the coastal system. So what do you think about long term, Yeah.
Yeah, no, I think that's an important addition to things I was saying. Yeah, so yeah, I mean, moving into the future as the channels equilibrate to those new conditions, yeah, it could shift in the other direction, quite easily.
Okay.
Yeah, I think that's a great point. Thank you.
John, Professor Anderson, John, yeah.
Yeah, great talk, Tony. How you doing? I was curious about the Texas data and the last slide you showed, your summary slide. And it's really pretty startling, the difference between Texas and the other locations, and in terms of the deficit of sediment there. I think obviously one factor would be just the lack of development in a lot of these areas, and my guess is that's a part of the question. But we also know that southern parts of Texas, central and southern parts of Texas, have experienced increased aridity during the last several decades. And just curious if you have any ideas about how much of a role those two have played in terms of making Texas so unique in this regard.
Yeah, I mean, I think the Texas, what's driving all of these points, the relative sea level rise is so high, and the estuaries like the Sabine, that's increasing in size. So we have more area to deposit material. And so the core record is also minimizing the mass accumulation rates and the sediment accumulations because we're smearing it out over a larger area. And so that's impacting things too. But to be able to say, is it the change in climate versus urbanization? For that North American data set, we didn't go in and look at land use change and explore that in detail. But that is something we can do in the North Carolina data set.
Great, thank you.
Okay. Anybody else? And Tony, I have a couple of questions. Let's pick up one first. And most of the research, the conclusion based on the nearshore, and water sediment accumulation rate from lake to 10. then you see that kind of post 1950 kind of accumulation increased. Then you draw a conclusion, here most of those coastal areas is not sediment starving. Actually, we see a increasing signal. Okay, that's good. And do you have tried to compare those accumulation rate with the import? Like any river have a long historical sediment flux discharge data to support. Of course, unfortunately, North American, we know that we barely have such kind of data, except some large river system maybe. So, I mean, how do you do a verification?
Yeah, it's a problem. Yeah, what you said is exactly true. The sites that we do have data are far above where we need the data.
Yeah.
So they might not be reflecting what we're seeing at the coast. And in a lot of the previous work, they're showing a decline. So they're not capturing this. So I do think that there's a disconnect there. So we don't have much that we can compare to. And those records don't go back as far, they don't go past 1950. So we can't really do this comparison, but we might be able to moving forward. We just need to install them, I guess.
Yeah. The other consideration is, in maybe future, some student can do, we can regroup of your data, some large river, over some small river. For example, in North Carolina, the News River, the Cape Fear River. And then we can see maybe the river discharge is consistent, is not changed, but because urbanization, because of human activity, we kind of deliver more sediment to the sea instead of let them to flooding around, in the delta plain. So now maybe we push those discharge more to the near shore or offshore, and in the bay. That's maybe one of the reasons we received more kind of, but actually the river didn't really increase any discharge.
Yeah, exactly. And maybe, yeah, so it could just be these tidal creeks that are compensating. So all of the modifications that we've made along the coast with these smaller systems that are more directly fed into estuaries in the coastal ocean. Yeah, that's a really good point. It could be that the rivers really have decreased, but it's these smaller systems at the coast that have totally compensated and overcompensated for that.
That's more, we need more kind of go deeper, that kind of study. And so very interesting. Anybody else? Even the Mississippi River, the channelization make the delta plain receive less sedimentation, but even reduced by the dam. But those 100 million tons, still majority of them was sent to the nearshore offshore. And anybody else? If no, I think that's a great work, great talk, and Tony, and it's very nice. So thank you very much once again. Our next week, Professor Elder come from Brigham University, come here talk about the ocean current, internal wave, turbidity current. It's also a global scale study. So do come here, join us next week. Otherwise, Tony, thank you very much. This is a very good starting point. And so very nice. Thank you.
Great. Hope to see you soon.
Okay.
Bye.
Yeah, bye.